Okay, greetings everybody. We are continuing our videos on the introduction of automatic control systems. So now in this video, I'm going to give you some very basic information about some fundamental system properties. Okay, now let's begin. Okay, of course, let's say we have a system. We need to somehow describe this system. Okay, so we need a model for this. And how do we describe a system? For example, this very small system here with a mass spring and a damper. Usually, the most fundamental approach for modeling a phenomenon is through a set of differential equations. Okay, so you may have one differential equation, or you may have more differential equations, right? And these differential equations relate and describe the relation between the input. Here is this function f, which is the force that we give to the system, and a variable state of the system. In this case, it is the displacement of the body. And of course, the differential equation includes the force, the displacement of the body, the velocity, which is x dot, and the acceleration, which is twice differentiation of the displacement, right? So this is one of the most classic ways to model a system, right? Through differential equations. Of course, if the system is discrete, you're not going to have differential equations. You're going to have what is called a set of difference equations. Okay, so this is the most classic way. Of course, as we are going to learn about in automatic control systems, we are going to use different methodologies for analyzing systems. Okay, so a secondary approach is through a state space description. Of course, I'm going to discuss about this analytically in another video, but the idea behind a state-based description is this. Okay, say you have a differential equation of higher order that describes a phenomenon. Okay, let's say it's second order differential equation or third order or maybe more, right? The idea here, and this idea was proposed by Kalman, which we discussed previously, is to use a set of first order differential equations to describe this phenomenon. And it is an equivalent set, so we don't lose any information. We just transition from a higher order differential equation to a specific number of differential equations of first order, okay, which we write them in this formulation right here, where u is the input, x is the system state, and actually it's not just one value, it's a vector of states, and y is the output of the system, which denotes some sort of measurable quantity. And A, B, C, and D are some matrices that have appropriate sizes. Okay. So one might think, of course, okay, Lazarus, what's the point here? Why isn't it better to have one differential equation of higher order than having far too many differential equations of first order? You know, upon first inspection, we may think that, okay, it's better to have one, even if it is a higher order. But in actuality, it's much better to have many differential equations of first order, right? Because here in the linear case, what you can do, and that's what Kalman proposed, is that you can do amazing stuff in analyzing the system and in controlling the system, but using matrix theory. Okay, and as we all know, matrix theory and linear algebra is it's taught in any engineering and mathematics department, is a very fundamental topic, and that's the idea here, to transition from calculus knowledge to linear algebra techniques and matrices. And this is an amazing way to model and control systems using state space theory. It is a separate subject, of course, and we are going to discuss about it a little bit later. Okay, so this is the second way of modeling a system. The third way of modeling a system, let me move this, okay. I don't want to talk about that. I'm going to discuss this example in a later video. So the third way of modeling a system is through what is called a transfer function. A transfer function is a very simple description. I would dare say the simplest of all the three descriptions. And it is basically a rational function where, the numerator and denominator are both polynomials with respect to specific variable. And this is an even simpler technique because it allows us a lot of analysis. Actually, this is the main part of the course because we can analyze the system and we can control the system not using differential equations, but using polynomials and rational functions. So this is an amazing technique, right? So all of these three techniques, all of these three models, differential equations, state space equations, and the transfer functions are actually equivalent. And by that, I mean that they describe the exact same model, and you can go back and forth in between them without losing any information. Okay, there is some very, very minor exception here, but I'm not going to discuss this. Okay, so in the general case, you can go back and forth and you don't lose any information regarding your system. Okay, so let's say you have a set of differential equations. Okay, you can use them to obtain the transfer function of the system. Right. And in a reverse way, if I have a transfer function that describes the system, equivalently, I'm sorry, I can go back into differential equations. Okay. And the same holds for state space. You can go from transfer function to state space. From state space, you can go into, I'm sorry, from differential equations to state space. You can go from state space to transfer function. You can go from a state space to ODEs. You can go from transfer function into a state space. So they are totally equivalent, and you can go back and forth into any of these descriptions. And of course, based on what you are familiar from other courses, you can also use control techniques from different perspectives and from different fields. So, if you're very familiar with working on state space and you have a lot of knowledge here from state space theory, if you are given a transfer function, you don't want to work with the transfer function. So what are you going to do? You're going to get a state space description and apply all your knowledge to controlling this system. Okay. And the same holds, of course, for any of these three descriptions. Okay. So those are the basics of system descriptions. We are going to give a lot of examples, of course, at a later video. Now, let's start talking about some other basic stuff. Now, the topic of the course, of course, has to do with continuous systems. And most of the systems in nature, of course, are continuous, and specifically mechanical systems, stuff like that, man-made systems are all of them continuous. But there is another very big family of systems, which are the discrete time systems. Now, discrete time systems, they don't, their evolution doesn't, we don't model them like a flow, for example, but we model them in discrete instances. And this is very common in systems where we may not entirely, observe them every single time. For example, how can I explain this? A mechanical system, for example, evolves continuously in time. But let's say you are looking at an economical model and you are taking some measurements at the end of each month. Okay, so you are observing the model at discrete instances every single month. Okay, so this model, it's better to be modeled and analyzed through discrete time. And the same holds, for example, in some population models. Let's say you are measuring the population every month or every year, for example, for mice or for foxes in a forest. Again, you're observing it in discrete times, right? So this makes much more sense if you are modeling this system in discrete time rather than in continuous time, right? So these are two very big categories of systems. And of course, there's a different property and analysis tools for each one. But of course, there is the case of going in between, where it has to do with discretizing a continuous system. And let's see, for example, let's think that we are having a continuous system like a mechanical system, but we are designing the control of this system inside the computer. So obviously, the computer works in discrete time. So in order to perform the analysis, I have to do some sort of discretization on the continuous system. Okay. And what I'm gonna do here is I'm trying to describe a discrete version of the continuous system, right? And I'm also performing some sort of sampling on the continuous system, ideally very fast. So here, for example, I start from sampling every half a second. So I'm starting from x0, x0.5, x1, x1.5, x2, and so on. Okay. So this is a classic sampling process. Of course, ideally, in mechanical systems, the sampling should be very, very fast. So this is not a good enough sampling. And again, this gives birth to a very big topic, the topic of accurate sampling and accurate discretization of systems. In itself, a very big topic in control theory. And this topic is, of course, very important because if you don't apply fast enough sampling of your measurements, you are going to end up with inaccurate model description. Okay, so this is, for example, a classic discretization. It's called zero order hold. You take a sample every so often, you decide that, and you keep this value fixed. And that's why you obtain this sort of staircase description of the system. And of course, if this sampling is done in a very fast time, this staircase will be closer and closer and closer to the original system, right? So this may be an accurate system discretization. But of course, if sampling is done uh, in very in very long time instances, and especially if the system has a lot of oscillations, for example, the discretization will give you a completely faulty description of the system. Okay, because see right here, the system oscillates a lot, but although the system oscillates, oops, I'm sorry, although the system oscillates really, really fast, we are applying discretization very slowly. So instead of having an accurate measurement of this oscillation, what we do is measure this value and this value and this value and this value and so on. So our discretization gives us this sort of inaccurate measurements for the system behavior because actually the system oscillates. But due to our very long sampling, we don't obtain an accurate description of the system. Okay, so this is a very classic example of very bad sampling. Okay, of course, this is not a topic in our own course, but in general, it is a very big topic in control theory. Now, let's discuss some very basic system properties. Okay, these are super fundamental. Let's start with the most basic one, causality. Okay, sounds very obvious, of course, and it is obvious. A system is causal if its output at any given time depends on the input up until this exact time, right? So, as you can understand, this sounds very obvious. So, naturally, in nature all around us, systems are, of course, causal because you can have a system that accepts output from the future, right? It makes absolutely sense. But still, in control design, you may encounter non-causal examples. For example, when designing control techniques like predictive control. Okay, predictive control is just like, say, for example, you are playing cards, like, say, Magic the Gathering or something else. You are establishing a technique based on the control or decision that you are taking right now, but also you are taking into account the actions that you are gonna take on the following terms, right? So you are acting right now, but you're taking into account your future steps, right? Of course, you're not breaking any continuous nature of the universe, but you're kind of taking the future into account. And this sort of idea is implemented in predictive control. But other than that, you're not gonna really establish and find non-causal systems. Okay. Now, the second super fundamental property, I mean extremely fundamental, is linearity. Okay. Linearity actually consists of two properties. A system is linear when it is homogeneous and additive. What does every property mean? Homogeneity in a system means this. Okay. Let's say I have an input, I feed it into the system, and I obtain an output. Right? Nice. So now let's say I make this experiment again, but I provide a scaling of this input to the system. Okay, so let's say I multiply my input by some factor alpha and I feed it into the system. Okay, if the system is homogeneous, the output of this system is going to be the exact same output that I had earlier, scaled by the same factor. Okay, so let's say I'm giving some force to the, let's say I'm having a system, I'm giving it some input and it behaves like that, right? If I multiply the input by 2, the output is going to be twice this output that you see right here. And I'm going to try and draw it. So the output is going to be, I'm sorry, I didn't draw it very well, but the output is going to be twice the original output, okay? So this is very important because once you obtain one simulation, you actually obtain information about many, many more simulations. So every scaling of this input is going to give us the same scaling of the output, right? So I obtain many information about the system. This is the first property that we need. The second property of the system is that it should be additive. The additive property means this. I have an input, I provide to the system, I obtain an output, right? Cool. Okay. Now, I have a secondary input, I provide it to the system, and I get another output. Cool. So what will happen if I provide to the system the addition of these two inputs, right? If the system is additive, the output in this case is going to be the addition of the two previous outputs, right? So this is an extremely interesting property and very helpful because imagine that we may have a system that has our own input and another unknown input that we don't know about it. Okay, so if the system is additive, what we can do, we can actually simulate the system using only our own known input, then compare this result with the case that we have an unknown input, and by observing this difference, we are actually able to estimate what is the result of the unknown input to the system. Okay, so these are very, very important properties. Of course, these are fundamental in linear systems. If the system has non-linear terms, these properties will not hold anymore. Okay, so this is just a simple example. Say I have a system that I provide a fixed input that you see right here, and I obtain this blue output. Then I give a different input, which is this one, okay, the gray one, and I obtain the blue output, right? So what will happen if I provide the system with the addition of the previous two? Okay, so I added this fixed value and this curved line. So this is my new input that you see right here. And in this case, the output is actually the addition of the previous outputs. Okay, so this output right here is practically this output right here and this output right here added together. Okay, so this is a classic case of a linear system. Now, another important result is time invariance. The system actually is called time invariant when when you switch the input and move it some seconds later, the output will not change in its shape. It will be exactly the same, but it will be moved on to some seconds later. Okay. So see here, I provide some input to the system and I obtain this output. So what happens? I provide them the same input, but I provide it 2 seconds later. So what happens? The output is exactly the same as before, but it is moved 2 seconds later in time. Okay, but other than that, the output is exactly the same. So it's just shifted in time a little bit later. Okay, so this is time invariance. Not all systems have this property, but the systems that we are dealing with are actually all time invariant. Okay. Now, another property is memory. Memory has to do with the fact that the output depends only on the input at this specific time. Okay. If this is the case, the system is memoryless. It has no memory. If there is another term, for example, integration term or something else, the system has memory. A classic example in this case is called delay systems. This is, for example, the case of a delay system. Now, delay systems are described by differential equations that include not only functions of time at a fixed time t, but also delays. So this is a delay term right here. Okay, it has to do with the value of y at time t minus 1, so 1 second earlier, right? So these are extremely hard to analyze. They are very interesting, of course, because they appear a lot in practice, and they are a very big part of the control community. Okay, so this is a case of a system that has memory. Okay, and another property is the dimension of the system. This is very important in state space descriptions. Basically, a system is called finite dimensional when for any derivative, the differential equation of the output depends or of the given state depends only on the previous on the previous derivatives of the input and output, right? So in any other situation, you may encounter that in more advanced topics, of course, the system is not finite dimensional. And in this case, we don't necessarily say it's infinite dimensional. Don't think that's correct. We simply say that the system is not a finite dimensional system, right? So this is again a very fundamental property. So these are all the basic properties that we will deal in this course. Of course, uh, systems that don't have these properties usually are much harder to analyze. For example, systems with delay, um, systems that are not finite dimensional. These are very difficult topics. So they are usually dealt with in more advanced courses or in a PhD level or in a research level, but they are a very big part of the control community, nonetheless. So finally, only thing I have to mention is that we distinguish systems in deterministic systems, which are the most common, and in stochastic systems. Systems mean that we either have some sort of input to the system that is described by a stochastic variable, or maybe some sort of parameter inside the system. We don't know its value, but it's time varying. And the only thing we know is some statistical characteristics about this parameter. Okay, so in this sort of situations, the system is called a stochastic system because it includes some sort of stochasticity, some stochastic term, either like a stochastic parameter or maybe some stochastic input or disturbance, right? Of course, this is not something we're going to deal with. We're only dealing with deterministic systems here. Okay, so this is a little stuff for this talk. Any questions, write them down. I'm going to answer you. So thank you very much. And I'll see you in a later video.